Finishing up section 7.5, we have a few more word problem examples that require us to set up the rational expressions in order to solve them and find whatever we're looking for. So our next example, we have a party cruise boat, goes 10 miles against, it's supposed to say against the current of a river in the same amount of time that it travels 15 miles with the current supporting it. If the speed of the current is 3 miles per hour, find the speed of the boat in still water. Alright, so this is a problem involving distances, speeds, and times. We're going to need to use the distance formula, which is distance equals rate times time. Okay, so that's one formula that's going to come into play with a lot of these examples we look at. Distance equals rate times time. So we can just use d, r, and t for the sake of our situation. So things that we know. The party cruise boat is going 10 miles per hour, going 10 miles, and takes the same amount of time that it travels 15 miles when it has the current. So obviously going against the current, it's making the boat go slower. It can only go 10 miles in the same amount of time that it can go 15 miles when it has the current pushing it. Also, the speed of the current in still water is what we're trying to find. So that's gonna kind of another important piece. Find the speed of the boat in still water. Okay. So, since we know it takes the same amount of time, okay, the time of the two trips are going to be the same. Okay, the time of the two trips are equal to each other. So since we know those two things are going to be equal, what we want to do is resolve this distance formula for t. Since we know the times are going to be equal, that's typically what you want to do, is solve for that variable. So if distance equals rate times time, if we divide it on both sides by r, time is going to equal distance divided by rate. So if we solve for t, coming over here, if we take distance and divide it by the rate, which is your speed, that's going to equal how much time it took. Okay. So we're still applying that distance formula, but we're kind of just manipulating it to help our situation. Alright. So now, and then also what are we finding? We're going to find the, excuse me, find the speed of the boat when it's in still water. Okay, so we're going to use our variable to represent this, because that's what we're trying to find. So we need a variable to represent that in this problem. So we can use x. You could use s for speed. I don't usually like using s's because it gets confused with 5s. So I'm just going to use x. Alright, so what we can do in these problems is set up a little kind of chart to kind of diagram the two different trips. Okay, we had a trip where the boat was going against the current and a trip where the boat was going with the current. Okay, so we first are described, the boat goes 10 miles when it's going against the current, and then when it's 15 miles is traveled when it has the current at its back. So let's describe these two trips. Okay, one is going to be against the current, then we have with the current. So for both trips, we want to talk about what is our distance, what what is our rate? And what is our time? How much time for each trip? Okay. So let's fill in some things we know. When we were going against the current, how much distance was covered? Well, we just said up here in the first sentence, 10 miles the boat drove or was riding against the current. Okay, so that's our distance, 10 for miles. When it had the current at its back with the current, it traveled 15 miles. So the second trip on the way back with the current, or maybe not back, but a second trip went 15 miles. Okay, the rate, now that's going to be the speed of the boat. Here's where we have to, we don't know the exact speed, but we can use it in relation to x, which is how, if the boat was going in still water. So if the boat's going against the current, that means the speed is slowing it down. So if the boat normally is going x miles per hour if it was in still water, if it's going against a current that's 3 miles per hour, okay, that current's going to slow the speed of the boat down by 3 miles per hour. So the rate, the speed when you're going against the current is going to be x minus 3. Whereas when you had the current at your back pushing the boat faster, that's going to be the speed of the boat in still water, x plus 3. Okay, because it's going to make the speed be faster when you have the current pushing it. And now time, how long did it take, during the trip against the current and the trip with the current? Well, we don't know that exactly. It doesn't ever tell us the exact amount of time. But now, because we have our distance and rate expressions, and up here we had solved for time. Time is going to always equal your distance divided by your rate. So we use what we solved up there to help us come up with the two expressions for time. So time is always going to equal your distance traveled divided by your speed or your rate. So for the against the current, it's going to be 10 over x minus 3. Okay. And then when it was going with the current, we do distance over time, distance divided by time, so 15 over x plus 3. All right. So now we have these two expressions that don't really help us any, except the fact that we know the two times are equal. It says that right here. And the party bus goes 10 miles against the current of the river in the same amount of time that it travels 15 miles. So if these are two expressions that describe the time against the current and the time it traveled with the current, we can set these two expressions equal to each other, since we know the time traveled was equal. So since we know the times are equal, we can set one expression, 10 over x minus 3. Okay, that was the expression for the trip against the current. That's going to have to equal the expression that we used to represent the time when we were going with the current, 15 over x plus 3. Okay. So, yeah, there we go. That's going to help us set up there's our rational expression. Now we have to solve this, one of the couple ways we talked about solving rational expressions. This right here is a proportion. Okay, we have a fraction equaling a fraction, so we can cross multiply. Okay. Cross multiply. So multiplying one diagonal, we get 10 times the expression x plus 3. And that's going to have to be equivalent to multiplying the other diagonal, 15 times the expression x minus 3. Okay, so So that saves us some trouble from having to multiply by an LCD on both sides. It's going to be easier when we just have it set up like this as a proportion. So go ahead and distribute the 10 and the 15 on the two different sides. We get 10x plus 30 on the left. We get 15x minus 45 on the right. Okay. I guess then we want to get our x terms on the same side. If we subtract 10x from both sides, it's going to cancel it out here and leave us just a 30. And then if we subtract 10x over on this side, it'll leave us just a 5x. When we subtract there, but minus the 45. We then are going to want to add 45 to both sides. Let's do that over here. Adding 45 to both sides is going to give us a 75 on the left-hand side and a 5x on the right-hand side. So we then want to divide by 5, divide by 5. And we get that x equals 75 divided by 5 gives you 15. But what is x representing in this problem? X is the speed of the boat in still water, which is what we want to find. So this, we want to write the units for the speed is miles per hour. So we found the boat going 15 miles per hour. It can go, when it was going against the current, which would then be minus 3 miles per hour. So when it was 12 miles per hour, it could go 10 miles. And the same as if you add it here, when it was going 18 miles per hour when it had the current, it could go 15 miles during that same time. But our answer is the speed. So miles per hour, 15. All right. All right, so that's one example using distance, rate, and time. The next example is going to need to use that same formula, but in a little bit different way. Let's take a look at that. We have that a private plane traveled from Houston to the desert at an average speed of 420 miles per hour. On the return trip, it averaged 300 miles per hour. If the total travel time was 9 hours, how far is Houston from the desert? Okay, so we again want to set up our distance, rate, and time situations. So we have our two trips. One trip to the desert, and then the trip back to Houston. Okay. So let's set up our chart again. We're going to have a box for the distance, a box for our rates, our speeds, and then a box for the time. Okay. So let's look at the problem. What do we know? Okay. From Houston to the desert, it was going 420 miles per hour. Okay. Houston to the desert, 420 miles per hour. So there's our rate. Okay. On the return trip back to Houston, it averaged 300 miles per hour. Okay, so the return trip, 300 miles per hour. So we have our rate for that trip as well. Okay. And then that's really all we're given. Except we're given the total travel time was 9 hours. So this is important. Total travel time, 9 hours. And the actual question then asking, how far is Houston from the desert? Okay. So the total travel time is 9 hours, but that doesn't mean the trip to the desert was 9 hours or the trip back to Houston. Together they have to add up to 9. So we have to get a little creative here. We don't know the distance traveled. Okay, that's what we're going to be trying to find. So we need some expression to represent our time, since we don't know how many hours either of the trips took. So we have to just assign a variable. So we can call the time to get to the desert. We can call it x or t for time, whatever you want to do. I guess I could call it t. Okay, so that's going to represent, t is going to represent how many hours it took for us to get to the desert on this trip. So then if we know the total trip took 9 hours, we don't know how long it took to get back to Houston, but we know that if we take 9 and subtract away the t, however many hours it took to get to the desert, subtracting that will tell us how many hours were left for the return trip. Okay, so if you think about it, if it took 5 hours to get to the desert, it took 9 minus 5, or 4 hours to get back to Houston. If it took 1 hour to get to the desert, it took 9 minus 1, or 8 hours to get back to Houston. So 9 minus t is the expression we need for the time to get back to Houston. Okay? And do we know the distance to get to the desert? No. Do we know the distance to get back to Houston? No. But since we know the formula distance equals rate times time, then we can, I guess, use that formula. So we can now fill in our distance to get to the desert was 420, our rate times the time. So 420 times t. And the trip back to Houston, that distance is going to be that rate times time, 300 times 9 minus t. Since it's two terms there that we're subtracting, we want to put that in parentheses. Okay. So we just figure that out just using, again, the distance formula. So let's now set some things up. We use the distance formula, but also we know from the problem that the two distances, I mean, it doesn't necessarily say, but if you take a trip to the desert and then a trip from the desert right back to Houston, these distances have to be equal. Okay? We know that just because it's saying you're going from Houston to the desert and then the desert back. So you're not really given that, but you have to kind of just imply that. So we know, let me write that over here. We know that the distances are equal. Okay, if I take a trip to Dallas and then a trip back from Dallas to Houston, obviously that's going to be the same amount of miles covered. Same idea with this desert. So because the distances are equal, well, we can kind of set up our equation then based off of that. So we can go 420t is going to have to equal the 300 times 9 minus t. Okay? Because those are the two expressions for the distances. So now we just work this out and we can solve for t, which finds us how long it took to get to the desert. So solving this, distribute the 300. That is going to give us, left side will still be 420t. 300 times 9 is 2700. 300 times a minus x is going to be minus 300x. Add, sorry, not x, 300t. Adding 300t to both sides is going to give us 720t on the left equals 2700, and it will cancel out the 300t there. We would then want to divide by 720 to solve and find out what t equals. Okay. So if we divide by 720, we can take that over here, and we end up finding that t equals 3.75. And what did t represent in this problem? T was the hours that it took to get to the desert. So hours. So did we find our problem? The answer to this problem, which actually going back up to the problem, how far is Houston from the desert? No, that's asking distance. how far in distance is it from the desert. So we have to use either of these two distance expressions because they're going to be the same distance either way. So use either of those two distance expressions and plug in 3.75 for your t. So the 420t expression, I guess, would be a little bit easier. So the distance is going to equal 420 times 3.75. Multiplying that out gives you 1,575 miles. So that's how far it was from Houston to the desert. That's how far it was from the desert back to Houston. Okay. So two different examples there of using the distance formula. Both obviously come up with different types of situation. One, you have to end up setting two fractions equal to each other, up top what we just did. This example ends up just being a linear situation right off the bat. Alright. We can go to the next example. Okay, whenever we deal with rational expressions, typically a work type example like this is pretty common to try to teach how it can be used in a situation like this to determine how long a job might take if you have two people working together. Okay, so our situation here is we have Letitia and Kareem are cleaning up trash in their community. If the same job takes Kareem 7 hours, that only takes Letitia 5 hours, how long would it take if they worked together? Alright, so kind of formula that you need to use for all of these work problems that's dealing with how long it took, one or two people to do a job, is that your work rate is always going to equal 1 over the amount of time. Okay. So let's talk about what we have here. Two different people, two different rates. So we have Kareem's situation. He completes the job in 7 hours. So you want to think of, well, if he completes one job in 7 hours, how much would he be able to complete in 1 hour? And that would be his rate. So 1 over the time, 1 over 7 hours is his rate. So essentially he completes 1/7 of the job in an hour's time. Or per hour, I guess we could say. Since it is a rate, you want to think of it that way. So if it takes him 7 hours to do the whole job, in 1 hour he gets 1/7 of the job done. Then we have Letitia, who's working a little bit faster. She only takes 5 hours to get a whole job done. So she's going to complete 1/5 of the job every hour. Okay. So in an hour, we have Kareem finishing 1/7 of the job. Letitia completes 1/5 of the job. So together in 1 hour, they complete 1/7 plus 1/5. Okay. So what we can do is we can let X equal the amount of hours needed to finish the job. To finish the entire job. Okay. So we have a couple different options here. I think the way I did in the notes might be a little bit more difficult, where you have to multiply by an LCD in that. But really, I think I want to approach this one a little bit differently because I think it can be easier. So if it takes Kareem 1/7 he gets 1/7 of the job done in an hour. It takes Letitia, or she completes 1/5 of the job in the hour. So together, they complete 1/5 plus 1/7 of the job. but we need to convert these fractions so they have a common denominator in order to add them together. Okay, so we'd have to multiply 7 times 5 to get 35, and 5 times 7 to get 35. Okay, that would be our LCD. So we'd also have to multiply the numerator times 7 and this numerator times 5. Okay. So that gives us that together they're completing 7/35 plus 5/35, which is going to equal 11/35 of the job. Or sorry, 12. Okay. So together, 12/35 is how much they're completing per hour. Okay. So if 12/35 is how much they're completing per hour, we want to multiply that by x times however many hours it takes to see what it would take to get them to complete one whole job. So what we want to do is, now we can set up an equation. Okay, they're both together completing 12/35 of the job. That amount times x, okay, times x hours, is going to have to equal 1 for one completed job. So however, the partial amount of the job you finish in an hour times the amount of hours is going to equal, is going to need to equal 1 for, how many hours will it take to complete the one whole amount of the job. So if you recall, when we have a fraction as our coefficient on x, we can multiply by a reciprocal, and that will cancel out the fraction attached to x. So we multiply by the reciprocal on both sides, flip the fraction and multiply. Or we could multiply on 35 here to cancel out the denominator, so 35 on both sides, and then we'd have to divide by 12 in the next step. So either way, you're going to get to the same answer. Okay. So we can go here with, if we have 12/35, x equals 1, multiplying by the reciprocal is going to require us to multiply by 35/12 on both sides. Okay. You'll see what happens when you multiply something by its reciprocal, it just ends up equaling 1. Right? These denominators, or these diagonally will cancel, these diagonally will cancel, and we'd just be left with 1x, or x. Okay. So we get here that on the left-hand side, we're left with an x equals 1 times 35/12 is just 35/12. So you'd want to divide that, and it tells you that it would take 2.9 hours. Okay? 2.9 hours to complete the job when working together. Okay, that is. So maybe make a note of that. This is them working together. All right. Like I said, we could do this a different way. Maybe look at my notes up on Blackboard, and you might find that you like that method better. I think this one might just be easier since we can just combine the fractions right away to see how much they both together get done per hour. So, all right, let's look at one final example. It's another work situation, so we want to use that same formula that the work rate is 1 over the time. Okay. So, let's see what we have here. You and a friend can fix a car engine in 2 hours working together. So this is different because we're told right off the bat how long it would take us to work together. alone, your friend would take 3 hours. So how long would it take you to fix the car alone? Alright, so this is a little bit different than the last example. But once again, we need something. How long would it take for you to fix it alone? That's what we're trying to find. So we want to set a variable to equal that. Okay, so I could use t, I guess, for time. So t is going to be the time, the hours, for you to fix the engine alone. Okay. So your friend here takes 3 hours. Yeah. Friend takes 3 hours. So we want to see what is their rate. How much would they complete per hour is going to be 1/3 of the job. Ourselves in this problem, we don't know how long it takes. But if t is going to be the amount of hours it takes us to fix it alone, then our rate is going to be 1/t. So that's how much of the job we are able to finish per hour. Okay. And we know that working together, it takes us 2 hours to complete this job. So we can kind of use the same sort of setup as up there, but it's going to be a little bit different. Well, let's maybe write that in. So yeah, together it takes 2 hours to complete the job together. So we can set up some equations here. Okay. Your friend takes 1/3 of, well, he completes 1/3 of the job in an hour. But if we multiply that times 2 hours, okay, that's going to tell you how much he got done in the 2-hour time span. Excuse me, he or she. Plus the amount we got done in an hour was that 1/t amount. Okay, we completed 1/t. That's how much of the job we completed. But if we multiply that times 2 hours, that tells you how much we completed in the 2-hour time period. And so these together should then add up to equal 1. Okay, we have the amount that both of us worked individually times 2 hours. If we add that up together, it should equal that we completed the one whole job. Okay, so mathematically that would look like 1/3 times 2 plus 1/t times 2 equals 1. So we need to actually multiply these fractions times 2. 2 times 1/3 gives us 2/3. Plus 2 times 1/t gives us 2/t equals 1. And now here we could try to combine these fractions and then do what we did up on the problem above, multiplying by the reciprocal. But since we have an equation here that's set up like this with 2 separate fractions, it might be easier just to multiply by the LCD on both sides. Remember, we can multiply by the LCD, the lowest common denominator, in order to cancel our denominators. So if we look at these two, our LCD, we have a factor of a 3 and we have a factor of a t. Neither of those factor out, so we can just kind of stick them together. Our lowest common denominator is going to be 3t. Okay. So that's what we want to multiply in both cases. Well, we have to multiply by that in every single term in this problem. So I'm going to rewrite the original problem, 2/3 plus 3 over t equals 1. So we need to multiply that first fraction times 3t. We need to multiply our second fraction times 3t. And then on the right hand side of the equation we also have to multiply by 3t. Okay. So then going through, when we multiply this times 3t times this fraction, the factors of 3 are going to cancel. Looking at this fraction, the t's diagonally, those will cancel. And then over here we don't have a fraction, so we don't have to worry about anything canceling. Alright, guess we can take this. Well, I guess we could take it down a step. T times 2 is going to give us 2t plus 3 times 3, because the t's cancel, it's going to give us a 9, equals 1 times 3t. It's going to give us 3t. So now we have a pretty easy expression to to solve for. I just realized I made a mistake here. This was supposed to be 2 over t, and I changed it to a 3 over t here. So it should have been a 2 over t, and then 2 times 3 would have given us a 6 right here. Okay. So apologize for that. So 2t plus 6 equals 3t. So I guess first step we could get the t's on the same side. So we could subtract 2t from here and subtract 2t from here so that it cancels out on the left. Let's take this up here. So 2t minus 2t gives us nothing. We're left with a 6 there on the left hand side. 3t minus 2t gives us a single t. And that right there is our answer. T equals 6. But what does t represent? T represents the hours that it would take to fix the engine alone. So t equals 6 hours, and again that's how long it would take to fix it alone if we were working by ourselves. Okay. So it took your cousin 3 hours, it would take you 6 hours. If together it took 2 hours. And that is the last little bit then of section 7.5, applications of rational expressions.